Okay, hello everyone. So I'm the Octave Cornet. I'm the director of the Centre de Recherche Mathématiques. So that's Olivier Lafitte, who's helping me keep the room quiet. And so I'm very happy to welcome you for this first Aisenstadt lecture by Bernard Derrida. So Bernard Derrida was born in Algeria, and he studied at the École Normale Supérieure, followed by a PhD in Grenoble in 1979. And since 2015, he's a professor at the Collège de France. His work has been rewarded with numerous distinctions, Grand Prix Ampère of the French Academy of Sciences in 2001. He's a member of the French Academy of Sciences since 2004. He's a Chevalier de la Légion d'Honneur since 2017. And he works in theoretical physics with fundamental contributions to the study of spin classes, diffusions in random media, and other subjects. And we are very, very happy to welcome him here at the CRM as Eisenstadt Chair. And he will give us today the first lecture on the importance of large deviations in non-equilibrium physics. And his series of lectures will continue next Thursday. So I'm very happy to...
Thank you very much for this kind introduction. So it's both a big pleasure and honor to be here and to give you this lecture. And also I want first to thank the whole place here, the whole institute, and the organizers, Alessandra, Luigi, Claudio, and Virginie, who made this meeting so interesting. So why did I choose this title? And the main reason is that more and more, especially for the last 25 or 30 years, physicists talk more and more about large deviations. Maybe mathematicians were working on it much longer before, but now it has become a tool, everyday tool for physicists. So I would like just to give you a few examples which are mostly related to statistical physics and to the second law or to the definition of free energy, to show you that these properties are very related to large deviations. Okay, so let me start with what was physics at the 19th century. And in the 19th century, physics was mostly deterministic. We're trying to find deterministic laws. But in fact, these deterministic laws were just due to the law of large numbers. So the idea of statistical physics is always to start with microscopic objects, like, for example, molecules of water, and just to try to extract or to derive the property in large scale, like, for example, a fluid or ice, or whether a system of particles will become a solid, a fluid, or things like that. But in the last decades, it has also become something where you, instead of talking about atoms, you talk about animals, individuals, and so on, and you try to extract large-scale properties from the behavior of a few individuals. Okay, so the reason why physics is so deterministic, physical laws, is because just you have a law of large numbers. So usually when you have typically n constituents, then the accuracy would be a sum of variables, and you would expect some fluctuations of order of 1 over square root n. And if you take a few individuals, about 1,000, typically the accuracy would be a few %. But if you take 1 gram of water, the number of particles is so large that the fluctuations are very hard to detect, to see. So as a consequence, the physical laws usually look very deterministic. But already, you see, in the 19th century, people like Maxwell, they realized that, in fact, these deterministic laws are only due to the fact that the system is very large. If you decrease the number of particles at some stage, you will see deviations from the deterministic laws and you will see fluctuations. Also, if you read this quotation by Schrödinger, you see that physical laws are always approximate, and their accuracy is based on the validity of the law of large numbers. So this is typically what happened, what was understood qualitatively at the end of the 19th century. Now, one of the goals of statistical physics, as I said, is to derive the properties of large systems given what you know about the behavior of individuals or microscopic atoms. So, for example, I give you the interactions between molecules of water, and then you would like to know whether it's a liquid or a gas or a solid. And you see, if you take a few atoms, there is no meaning to say that it's a gas or a liquid, or it has no meaning. So in somehow, the large system looks different. You see, the more is different is a quotation of Phil Anderson, is that if you look at a system on big scale, then it has very little to do with what you would see if you would look at a few atoms or a few individuals. So as I said, if you look at a liquid, then it is very different from a few atoms. But if you look also at the insulator or conductor, you see it's hard to see how it's related to the property of copper atoms or things like that. The same with traffic jams, collective human behavior. If you look at a few neurons, it's very hard to talk about intelligence or things like that. So you see, at large scale, then the system is different. And one property I would like just to explain is that the arrow of time is also of this kind, that physical laws, if you think of atoms, physical laws have no arrow of time at the microscopic level. But at a macroscopic level, you see irreversibility. And so this is something I want to discuss, because later on I am going to talk about second law and irreversibility. And so irreversibility and the arrow of time is just a macroscopic effect. And to see it, you see, I just consider what physicists would do is I take a very simple situation where you have irreversibility. So in our daily life, of course, all the time we see irreversibility, like when you break eggs. But for the physicist, one way to think of irreversibility is to think of putting some atoms in this container, and with particles, all the particles on the left side, and then you let it evolve. There is no randomness at the microscopic level, just particles would be like small balls or small spheres which have just elastic collisions, and then you let it evolve, and then what you would see, is what you expect, is that when you open when you open the separation between the two sides, and the gas will fill the whole volume, and you will never see the situation backwards, although the collisions are very deterministic. And that's a question, in fact, which has, of course, been answered a long time ago, and I am going just to mention the answer very quickly, is that if the laws, like collisions between two spheres, are reversible, that is, if you take a movie of a collision of two spheres and then you look at the movie backwards, then you would see exactly that it satisfies all the laws of physics. So you would not see any difference between the movie one way or the reverse. So given that the physical laws are reversible, why do all macroscopic events have a preferred time direction? And if you take this example here of okay, it does not work too well, but if I take this example of the gas, the expansion of this gas, you will understand it very quickly. So in order to think of it, imagine that I start with a very small number of atoms on the left. And I would say, if there is an arrow of time, I would see that the gas will spread between the two sides, and then it will remain like that forever. But it is not what will happen. If you have these collisions, you have 5 atoms, and you wait not so long, you will see a situation where they come back. So somehow you would see that. So if you look at one direction of time on the other direction of time, it will look very reversible. But if you just increase the number of atoms, it will take much longer to come back to the initial situation. And in fact, a rough estimate is just that each time you increase the number of particles by 10, then the time to wait in order to see the initial situation will be multiplied by 1,000. So essentially, if you have 200 atoms, which is not so large compared to the number of atoms in a gas, which is extremely small, then already the recurrence time would be the age of the universe. Okay, so this is the irreversibility, and there was a long discussion, of course, because there is this Poincaré theorem that you know that any initial condition will come back, has to come back one day near its initial condition, but the answer, and so in principle, this would be against irreversibility, but the answer by Boltzmann, you see, I just summarize it very briefly, is that in fact, the recurrence time to see the system back to its initial condition would be so large, and so it's a huge time, and also if you just change the position of one particle due to the chaotic behavior of one particle in the initial condition, then the time to come back to the initial condition could be multiplied by 10 or by, would be completely different. Okay, so this is about irreversibility, and it will come back later on. Now, that at the end of the 19th century, you had these physical laws which are deterministic, and then at the beginning of the 20th century, and in fact, the whole 20th century has to do in physics with fluctuations. It has become a very important aspect in critical phenomena, for example. But here I will discuss just one aspect, which is due to the Einstein fluctuation, Einstein relations and fluctuations. Okay, so there is this paper by Einstein, which is in 1904, probably it was written in German, but this is its English version. And essentially, it said, if you have a large system, whatever system, large or not, if you have its energies and the energy of a system at equilibrium at a certain temperature, its energy will fluctuate. It fluctuates, it is at equilibrium at a certain temperature because all the times it exchanges energy with the outside world, and then its energy will fluctuate, and he wrote the equation which is on the left that I have rewritten on the right. Just the main difference is just the definition of K. K is a Boltzmann constant, that the variance of the energy of a system is just related through this parameter K. T is the temperature, to the derivative of the energy with respect to temperature. So this is an Einstein relation, and it's very general. It is not limited to the energy, but it is valid for all kinds of quantities. So in this formula that I wrote again, then E is the energy. I'm sorry, I made the sprint there. T is the temperature, K is the Boltzmann constant, and the Boltzmann constant is essentially what the inverse of the Avogadro number. And Avogadro number just tells you how many particles. It tells you how many particles you have in a gram of water, or a few grams of water, of matter, sorry. And it is essentially, it tells you the size of the atoms. So measuring K is a way of measuring the size of the atoms. And this was, in fact, the motivation of Einstein was to try to measure, or to have a way of predicting the size of atoms just from this fluctuation theory relation. Okay, so if you think of this relation, what does it do? Then it relates the response of coefficient, the derivative of the energy with respect to temperature is just the response to a small change of temperature to the variance of the energy. Okay, and the factor is K. But this relation relating the variance of fluctuations to a response is valid for all kinds of quantities of the currents. For example, if you have a current through a resistor, or there is also the Q2 formula, which is also a generalization of this relation for current. The position, the fluctuation of the position is related. In fact, the theory of the Brownian motion of Einstein is a kind of relation like that. You have transport coefficients on Sager relation and so on. It's something which is very, very general. So it's not limited at all to the energy. The main reason why a relation like that, so the variance of a fluctuation is K is the Boltzmann constant times the response coefficient. The main way to derive it is to assume or to write that the system is at equilibrium. And in fact, so let me just give you an example, which I don't know whether you see in a mathematical audience, even in a physical audience, I am not totally sure that everybody knows it, but it has been known for 80 years. That's what's called the Johnson-Nyquist noise. If you take a resistor, there is Ohm's law. Probably everybody has heard about Ohm's law, which relates the tension to the current, and R is the resistance. This is Ohm's law. So you expect that if you have no current, then if you open this circuit, then there is no current. So you expect that the voltage at the two ends of the resistor is zero. That's Ohm's law. But in fact, in the 1920s, in fact, it was realized that if you just open this resistor, then the tension, the voltage will fluctuate. And the way it fluctuates is like this, is the fluctuation of the tension in time. Okay, there is this delta function in time, but essentially is proportional to the resistor with this K in front of the Boltzmann constant. So this is essentially the story about the Nyquist noise. There is, okay, I would like also to mention something which played a very, very important role in physics. And it was the first step in the introduction of quantum mechanics. So maybe, okay, probably you have heard of that. The first step was what is called the Planck's law. Planck's law is just you have a black body and you measure how much energy there is in this black body at a given frequency of the radiation. So, okay, so it has this shape like this, and Planck's law is just this formula, which tells you that at the frequency nu, then the average energy at frequency nu is given. So nu is essentially the inverse of the wavelength. The energy is given by this formula, and h is what's called the Planck constant. And this is the first step about quantum mechanics. And in fact, it was somehow, I hope I remember it correctly, it was just trying to fit the data. So here you have the data at different temperatures, and the data could be fitted by this formula. Now, what did Einstein do with this formula? Then he used the relation, the Einstein relation, which is on the left there. And of course, it's not very difficult to take the derivative of this formula with the temperature. And if you do that, so you take this formula, you make the derivative with respect to temperature, so that's very easy. And you get, okay, when you take the derivative, you get that the fluctuations of the energies, the variance of the energy is just given by this expression. This is, so on the left, I just use this relation, and on the right, I have computed the derivative. And this has a very deep implication, because I don't know whether you heard about quantum mechanics, but in quantum mechanics, there is this duality. Should you consider an object like a particle or like a wave? And when you look at this relation, then in fact, if you had only particles, each particle having an energy h nu, you would have the first term here. If you would have only a wave, you would get the second term. And somehow this fluctuation tells you that you have both a wave and a particle. And if h nu is very large, so at very high energy, at very small wavelengths, then essentially the first term wins. So you have particles. If you are at low, at large wavelengths, like for example, Hertz waves or something, then it looks like waves. But this is a formula which shows you this duality. Now, as I said, Einstein was interested trying to use this fluctuation relation in order to guess, to have a way of measuring or predicting the size of the atoms. So let me just give you how, from this relation, you would get the size of atoms. And then I do it with a very simple example that I think it's easy to understand. Imagine that I have a gas or a liquid or whatever, and that this gas is made of particles. And here I have put particles essentially at random. And I ask how many particles I would see inside this subvolume, red subvolume. Now, if I look at this, you see in these subvolumes, particles will collide, and then some particles will enter, they will leave, and so on, and you would have a whole evolution. And so what you would see is that the number of particles inside this red region would evolve in time and would fluctuate. Now, imagine that I do the same, I look at the same system, but the system would consist of much smaller objects. Then the answer is rather trivial, is that the fluctuations would be much smaller. So in fact, if you take an ideal gas, and it would be slightly different for a true gas, but if you take an ideal gas, the variance of the number of particles inside the red region would be just, the variance would be just proportional to the total mass times the mass of the atoms. So the smaller are the atoms, the smaller will be the fluctuations. And so if you are able to measure the fluctuations, then you are able to tell what is the mass of the atoms. Okay, so essentially that's a cartoon just to explain the idea, but you can do it with the energy or with other things, and the story is the same. Now let me come to the large deviations. Okay, and first I come back to this relation by Einstein, but the way it was obtained was essentially an idea of large deviations. And the thing is, if you imagine that you have a large system, and then it has a large isolated system, and then you have a certain energy in a subregion here, and then the rest of the energy is left to the outside. And then you just, in fact, the way to derive it is just, he used the famous Boltzmann formula, that is the entropy is just K times the log of the volume of phase space. Now, you can ask, what is the probability of observing an energy E in this subsystem, in this red region? Essentially up to boundary effects that which would be negligible somehow when the size of the system is large, then it would be the entropy, the volume of phase space in the red region with this energy E, and times the volume of phase space in the outside. And then if you replace this W by exponential of S, then you get this expression, and then you ask, so this expression is typically a kind of expression of large deviations. And if you, so if you look at what is the equilibrium property, you would look, because k is so small, you would look at the place where the exponential is maximum, so you would find the average energy. But if you are interested in fluctuations, then you are going to expand around this maximum to second order, and then you would get the Einstein relation. Okay, so now the thing I am going to try to do is to come back to the density fluctuations and somehow to try to relate it to the free energy. Okay, but there is a calculation or an estimation which was due to Chandrasekhar, which is which in fact he also got the Nobel Prize, and he was in 1943. He wrote the following thing, that he asked, if you take a fluid or a gas, so you say a gas, and then you take a small region, a region of radius A, and you ask how long I need to wait in order that I see a small deviation of density inside this gas. And I find these numbers very surprising. You see, although you can make estimates once you have the idea of thinking of it, you can make these estimates. It's not too difficult. But yes, okay, if I look at a small region of a sphere of radius A, how long I have to wait in order to see density fluctuations of order 1%. Now, if the radius is 10 to the minus 5 centimeters, it's very quick. You would see it very quickly. But when you increase the size of the radius, but you see, if you increase it from 2 to the 2.5 to 3 or something like that, okay, then the numbers increases very, very quickly. And very quickly, you see that the time would be huge. And this means that it's a very, very rare event. So large deviations have to do with rare events. And here it's a case where you can estimate how long it would take. And the age of the universe is somewhere. That's at equilibrium, of course. Okay, so now the thing I want to do is to tell you that large deviations and free energy is a concept which has a very long history in physics, which was introduced in the 19th century, but essentially the two things are very similar. And I am going to try to convince you of this fact. So what is the free energy? In physics, the free energy is how much energy you would be able to extract from the system. For example, when you go from the left situation to the right situation. You see, if I just open and I leave it and I let it evolve by itself, then I will not gain anything. But if I am smart, you see, I can use the fact that the gas is going from the left to the right to extract some useful energy. For example, I could produce electricity, or if I prefer to travel, I could also do that. And so the free energy is how much, the maximum I could extract in this operation. I cannot extract everything because initially, you think the system is at a certain temperature, and then initially, okay, sorry, think that the system is isolated, then initially, there is a lot of energy because there is a kinetic energy of all these particles. And then when you let evolve, you are not able to get all this kinetic energy. You will just be able to get a little bit of this kinetic energy, but not all. And this is the work that you will be able to extract. And in fact, in the case of an ideal gas, this is a standard calculation. You can show that the maximum you can extract, the maximum energy you can extract from this is just written. You will not be able to do better then nkt times the log of the ratio of the volume. This is a very standard calculation, and this is also known, has been known from the 19th century. Okay, so now it turns out that, imagine that you have the same gas, it has a certain density rho, and you ask, so there is no gravity or anything, so the average number of particles in a certain subvolume will be just 0, but you could ask, what is the probability that in this subregion, I would see a density which is not the density outside, it is a density R. So what is the probability that I observe a number of particles which is atypical in this region? And okay, if the volume of the subregion is large enough, you expect something like a large deviation. You expect that this probability would be exponential V times a certain function d of R. And this function d of R, in fact, for a system at equilibrium, is just simply the free energy. So if you know the free energy, you can get the large deviation function of the density inside a subregion. And the formula is given here. Okay, it's a free energy back to a small derivative, but the free energy is just for a system at equilibrium related to the large deviation function of the density. And in fact, to prove it is rather easy, is that if you ask what is the probability that I see small n particles in this subvolume, it will be essentially the partition function of having n particle in the small volume V times the partition function of having n minus small n here, it should be small n, so the rest of the particles outside in the big volume, and then divided by the total partition function. And when you replace the partition function by the exponential of the free energy, you end up with the formula I wrote before. So the fluctuations of the density is essentially the free energy. Now, something about more recent things concerning this fluctuation of the density. A lot of work has been done over the last 20 years and even long before, but a lot of interest has concerned not systems at equilibrium, but system out of equilibrium. So one way of thinking of the system of equilibrium is imagine that I have again my gas here, say here a low density, high density, and then at time 0, I start to let them communicate. But the two sides, the two boxes on the sides are so large that essentially it will take very, very long before their density will change. So essentially what happens is that in the middle, you will reach a steady state. So at some stage, nothing will depend on time. And then you are interested in what happens in this system, which is in contact with two reservoirs at two densities. So the picture is the following, is that you have big reservoirs, one with density ρ1, the other one with density ρ2, my system in between, and I can ask, what is the probability, I take a subvolume very much as I did, what is the probability of seeing n particles in this small volume V? And we just show that if the system is at equilibrium, so what would be equilibrium here is that the two sides are the same density, so there is no current at all, then it would be the free energy. And you can ask, what is the probability of seeing a certain number of particles in this subvolume when I am out of equilibrium? And this is somehow a way of defining a free energy for a non-equilibrium system. Now, one property, and there has been a lot of work on these things, and for example, Claudio has been very active on such problems. And one particular thing is that it becomes, these large deviation functions becomes non-local. In the following way, if I ask, what is the probability of seeing a certain number of particles in the first box, in the second box, at equilibrium, the two things, it would be just the sum of what happens in one box and in the other box. That would be it. But if the system is out of equilibrium, then it's no longer the sum of the two. It becomes non-additive. You have long-range correlations, and people have tried to compute such things over the last decades or something. So this is some. So in other words, these large deviations of the density, you could do the same also with large deviations of the energy. Somehow they are an extension of the idea of free energy to non-equilibrium steady states, but they have different properties. And one major property is that it's no longer additive. You have this kind of long-range correlations which come from the fact that it's out of equilibrium. Okay, now in the last part of this talk, and I think I was a little too fast, I want to come back on second law, which also is something from the 19th century. And the second law is something which also reappeared in these last decades in the context of large deviation. So let me remind you what second law is in thermodynamics. And second law tells you the following. It says that if you have your gas on the left, you wait and the gas will spread through the whole volume. And you will not see there is some arrow like this. And there is maybe another way, another situation that if you take a glass of hot water and cold water, you put them together and it will become warm. And you will never see the situation where you have the warm coming back to cold and hot. Okay, so that's second law. And okay, we can check it every day in our life. And I am sure that you have never seen this arrow by itself unless you use energy with your fridge or something. But otherwise, if you let it do, you will not see it. Okay, so this is impossible. Now, I like to quote these two sentences, to give you these two quotations. And one of them is the second law. It was considered as probably the most perfect law in physics. And it was also supposed to have physical import. So it has been hailed for providing a proof of the existence of God. And so it has also been rejected as being incompatible with dialectical materialism. And this quotation by Einstein is that it says that it's the only law which will never be overthrown. So it's considered as one of the strongest laws of physics. The fact that when you have hot water and cold water, it becomes warm. Something. Okay, so one way to formulate it is the following, is to say, imagine, again, I have this kind of steady state. I have my system, and my system is in contact with a hot on the left and a cold on the right. And you expect that the energy, very much like when we had a glass of cold water and hot water, then the energy will go from the hot to the cold. Then if you have a system in contact with two heat baths at two different temperatures, then you expect that the energy will flow from the hot to the cold. And this is what is used everywhere, for example, to produce electricity or something. It's very much like the wind we had between the two boxes before, where we had the high density and the low density. It's very much the same. And so the fact that this energy here is positive, it's an inequality, and this reflects the fact that there is an arrow of time. You see the energy going in one direction, and if you would make a movie, you would not, you would see the energy going in the other direction, and you would immediately realize that there is something wrong, because you would see the heat going in the wrong direction. Okay, now, if I come back to what I discussed about the fluctuations, then you could consider several coefficients, several response coefficients. One response coefficient would be, imagine that I am very close to equilibrium. If I am very close to equilibrium, then the heat flow from the temperature T1 to the temperature T2 will be proportional to the difference, when the difference is very small, proportional to the time we observe, and then there will be a coefficient D, which is a response coefficient, how much energy flows responds to this small temperature difference. Very much like there is this Einstein relation, even if there is no temperature difference, because of the Einstein relation, this Q will not be constant. It will fluctuate. You will, from time to time, have some energy which goes from the right to the left and then back to the left, from the left to the right, and so on. It will fluctuate. And because of the Einstein relation, then you expect that the fluctuation of this energy would be proportional to time, because after all, if you wait long enough, there is some relaxation time in the system, and then you have independent events. And then there is this Boltzmann constant in front, and the D, the same coefficient appears. So this is very much like an Einstein relation. So already, just because the Einstein relation, you expect that if the system is at equilibrium, then you will have some heat going in both directions, fluctuations of heat. Now, so this is an Einstein relation. Now, what was obtained in about 25, 30 years ago is what's called the fluctuation theorem. And the fluctuation theorem says something about what happens in a system which is in a steady state. So imagine that you have these two temperatures, you let energy flow, but the two reservoirs are so big that even if there is energy which flows, then the temperature will not change. So the system is very large, the reservoirs are very large, and imagine that you measure how much energy has moved from the left to the right during time t. Now, what second law tells you is that this energy is positive. Now, you could imagine that you repeat this experiment or this measurement many times. So you are going to do it once, you will get Q1, and then you do another measurement, you will do Q2, and so on. And why this number fluctuates? Imagine, for example, that the system is very small. You have a few particles, a few atoms in my system. So these atoms, they move around, and from time to time, the only time they will see the left reservoir that they collide there. They exchange some energy, so somehow their kinetic energy is modified because they are in contact with the left reservoir. They come back, and the same on the right. And so you expect that if you have very few particles, then the number of collisions, if you repeat the experiment, then the number of collisions will not be exactly the same. The exchange of energy at each collision will not be exactly the same. So you expect that this Q1, Q2, Qn will be different if you do many experiments. And so you can talk about the probability of Q. And now what the theorem, fluctuation theorem says is that if the system, if you wait for very long, then the probability of seeing Q in one direction divided by the probability of seeing minus Q, so seeing the energy flowing in the wrong direction, is given by this expression. So, okay, so this is, again, you have exponential of something. This is a large deviation relation for the probability of Q. Now, there are a number of comments. You see, you have this relation, but one thing is that first, it's linear in Q. The second thing is that I did not tell you what system it is, because it's true for all systems. That is, it could be a solid, it could be a gas, it could be whatever. It's any system, and it's linear, and it's the same coefficient. You see, the coefficient is just independent of the system, and it contains only the two temperatures. now, one other aspect of it is that it tells you that it's a probabilistic character of the second law. That is, because this relation is true, if you expect in second law to see that Q is positive. But in fact, because of this relation, you should observe events where the Q is negative. They have to happen. That's the first aspect. The other aspect is that you remember the second law is an inequality. That is, Q is positive. The energy flowing from the left to the right, which is something which was discovered in the 19th century, is positive. But so it's an inequality. But here you see that this inequality becomes an equality because there is no unequal symbols there, signed here. One other thing, also it's important for physicists, is that experimentally it has been observed, and in fact, if you want to be a little more precise about the meaning of it, is that mathematically it would be more like you take the probability that Q equals JT divided by the probability of Q being minus JT, you take the log 1 over T, and in this limit, you would see that. So you see, it's a very general law, and it's an extension of the second law, and it has a large deviation aspect. Okay. Now, of course, what happens is that the fluctuation theorem, one thing is that what you expect in this situation here, again, the system in contact with two reservoirs, is that the probability that if you observe for a very long time the heat, the energy flowing from the left to the right, the probability that Qt over T is J has a large deviation function minus T f of J. And the typical shape of f of J, of course, f of J cannot be negative because it's just a probability, it could not be larger than 1. So f of J is positive, and at the typical current, it should vanish. This is the most likely situation. And so if you imagine that it has a shape, you see usually functions, which vanish and remain positive, usually they would look like a parabola near, they would look like a parabola near the minimum. Then if you just do that, then essentially you would see that you have Gaussian fluctuations of the current because the exponential of a parabola is a Gaussian, and you would be able to recover the Einstein relation just by looking at the minimum of this function. Okay, so maybe I was a little too fast, but I would like to conclude here. And so you see, I have large deviations now are something that people look at very much in statistical physics and in physics in general. One reason they are interested in large deviations is that is a way to estimate the occurrence of large events, of rare events, sorry. The other thing is, of course, in mathematics, it plays a very important role. In chemistry, it has to do also with people are interested in reaction paths. You see how long you will need to wait in order that the system will go above a certain barrier, things like that. And in physics, as I tried to show you with these two simple examples, it is related to the free energy, to the fluctuation theorem, to the second law, and it also appears in many other situations, like, for example, growing interface or something like that. And there are a lot of calculations on large deviations in the recent years, but I just decided just to present this a few examples here because I don't know how much the audience is familiar with these ideas of physicists. So I'm going to stop here and thank you very much for your attention.
Thank you very much, Bernard, for this nice talk. Is there any question or comment?
Did you say that QT was positive even after equilibrium?
QT is the energy which flows.
Yes.
No, at equilibrium, if you are at equilibrium, QT, okay, if the system, according to the second law, QT would be zero, exactly zero. But due to fluctuations, there is QT going one side.
Oh, okay.
It fluctuates.
Yes.
So it's,
Okay, thank you.
and it has a zero average.
Merci.
So, Bernard, essentially, the point is that the time of reversing the direction of energy goes to infinity when the number of particles goes to infinity, say. This would be the irreversibility.
I don't know. Okay. No, presumably, when this is, yes, of course, if the system is very large, you are closer and closer to the deterministic law. So you will never, okay, the probability of seeing the flow in the wrong direction would become smaller and smaller. But if the system is very large, then if you take the fluctuation theorem, you have this Q. So here. So yeah. if the larger the system is, the larger Q is, the smaller P of minus Q is.
Yeah, I just have a question. Sometimes moderate deviations are studied. Is there a connection in the physics with moderate deviations, those just beyond the central limit theorem, but not quite at large deviations?
It depends what you call moderate deviations. You see, so there are a number of interesting situations. For example, what's called the KPZ equation or things like that, where you see what I have drawn here is oversimplified. That there would be a whole law here, like in the KPZ equation or in the exclusion tacet or something like that. And the fluctuation of the current would have a whole interesting law with, so I don't know whether you refer to that when you talk about moderate deviation. So
so central limit theorem would be like 1 over square root of n, and then large deviations is further deviations away, but in between those scales.
Yes, okay, so this is typically the situation, for example, of the KPZ equation, where you see that there is a universal law which appears here. That's an example I have in mind, but maybe there are others, I don't know. There are better experts than me here.
You said your fluctuation theorem can be experimentally verified, which I find amazing, for mesoscopic. So how big are those mesoscopic systems? What are those kind of systems where you can actually measure the probability of minus Q?
Okay, so one thing, for example, I am sure I could do it myself, is to do a computer simulation of it. It is, I just take particle, you see, even you take an ideal gas or something like that. Yeah. And then so you have a number of particles and then you move around, and then when they come back here, they are reflected with a new kinetic energy, and which comes from something which has to do with the Boltzmann distribution here. So it comes back, and okay. So to do a simulation like that, and of course, if here it's hot and here it's cold, then it's hot. Usually you come back with a larger kinetic energy, but sometimes the Boltzmann distribution is such that sometimes you have events that you collide here, right. You come back and you get a small kinetic energy. And on the other side, the same could happen, is that although it's cold, it could happen that sometimes you collide and you come back with a high kinetic energy. So the combination of the two might allow energy to flow from the left to the right. Mm-hmm. I think people have looked at, now in experiments, I think they have looked at small small systems like DNA molecules or things like that, where they made these experiments. You see, there is, okay, here I talked about the fluctuation theorem. There is what's called the Jarzynski relation also. I don't know whether you heard of it, which, okay, maybe I did not want to talk about that, but you see, I don't know, after all. So you see, the second law, another way of saying second law, is that if you take a system, you let it, you modify it, and then you come back to its initial condition. So typically, for example, the physicist would say, here I have a piston or something like that, I move it, I come back. And I come back to the initial condition, exactly. So whatever I do, according to second law, is that it costs you some work. The best you can do is that it will cost you some work. Yes. Now, there is a relation due to Jarzynski who said, in fact, if you repeat the thing many times, then you will not get exactly the same work, because what is the work? What is the work? The origin of this work? You have these particles, and you have work. Each time you collide the particles and you push it, and then there is work. You see, if by luck, for example, you push it at a time that all the particles are on the left, you have no work at all because they have no resistance. Okay, so this work will fluctuate. Of course, if you have 10 to the 25 particles, you will always collide the same number of particles. But if you have a few number of particles, okay. So the W, if you repeat the experiments, the W will change. And Jarzynski wrote a formula like this, that if you repeat the operations many times, then this average, beta is the inverse of the temperature, this average is 1. Which means if you want this to have an average 1, and typical situations is W is negative, you should have events where W is negative also. And this, they have checked it because they take some DNA molecule, so very small molecule, and they pull on it and they come back. So these are experiments which have been done. Now, I should say for this case, I don't remember at the moment precisely the experiments which have been done.
Thank you very much.
Any other question? So let's thank Bernard.